So frequently, we are faced with the problem of describing a quantity that is zero everywhere, except at a single point. And at that point, it is infinite in such a way that its integral over any interval containing that point has a finite value. Okay, and for this purpose, it is useful to introduce the Dirac delta function. And the Dirac delta function is defined as, so let us start with the one-dimensional Dirac delta function. Okay, the one-dimensional Dirac delta function, Dirac delta function is defined as this is the Greek alphabet delta x. This is equal to 0 when x is not equal to 0. I repeat, for all values of x which is not equal to 0, the value of the function is 0. This we call equation number 1. And the second point is integration from minus infinity to plus infinity delta x dx. This is equal to 1. We call this equation number 2. Okay, this is fine. So this equation, it implies that delta function must be an infinitely high thin spike at x equal to 0. I repeat, this equation means that the delta function must be an infinitely high thin spike at x equal to 0. This is similar in the description of an impulsive force or the charge density for a point charge. Okay, so let me write it down again. These two expressions indicate that the Dirac delta function delta x is a singular function which vanishes everywhere except at x equal to 0, which vanishes everywhere except at x equal to 0, and its value at x equal to 0 is so large, and its value at x equal to 0 is so large that its integral over an interval containing the point x equal to 0 is unity. That means the integration is equal to 1. Okay, this is fine. Okay. Indeed, this delta function, it usually does not occur alone, but only in combinations with a certain function f of x. Because in the real sense of the word, delta x is not a function at all. It is a distribution. In the real definition of the function, delta x is not a function. We call it a distribution. Okay. Okay. So let us take a function f of x. Suppose I have a function f of x, which is defined at the point x equal to 0. So if we have a function f of x, which is defined at x equal to 0, then the action of delta function delta x to fx is equal to f of 0. This can be expressed by an expression. This can be expressed by an integral of the form, then integration from minus infinity to plus infinity. F of x delta x. F of x delta x dx. F of x, there we multiply by delta x and then we integrate from minus infinity to plus infinity, and this is equal to f of 0. Okay, this is equal to f of 0. This is what I mean by the sentence that the action of delta x on fx is equal to f of 0. Where f of 0 is the value of the function f of x at the origin. At the origin. Okay. This is fine. So I have f of x multiplied by delta x and I integrate over all space, over all values of x, I get f of 0. And f of 0 is the value of the function at the origin. An operation of this type, an operation of this type which assigns a number to a function, which assigns a number to a function is also called a functional. However, an operation of this type which assigns a number to a function is also called a functional. However, what happens if we shift the origin? See, instead of x, what happens if we have x minus a? So let us see. If we shift the origin, origin of coordinate system to x equal to a, then what happens is integration from minus infinity to plus infinity f of x delta x minus a dx. Delta x minus a dx, this is equal to f of a. This is the value of the function at the point x equal to the a. This we call equation number 4. Okay. Now let me take a new sheet of paper. Okay. Here, let me write down. Here, it is not necessary that the range of integration of equation number 3 and 4 be always from minus infinity to plus infinity. Here, let me come back to equations 3 and 4. Equation 3, equation 4. Here, it may be mentioned that it is not necessary that the range of integration of this equation 3, that is the range of integration here we have taken from minus infinity to plus infinity. Here also we have taken from minus infinity to plus infinity. It is not necessary that this range of integration be always from minus infinity plus infinity. It may be over any domain surrounding the point at which the delta function is not zero. That is, in this particular expression, the delta function is not zero when x is equal to a. Okay, so in this limit of integration, we can take any range which surrounds the point x equal to a. Similarly, here the delta function is not equal to zero at x equal to zero. Oh, so here as the range of integration, we may take any point surrounding the point x equal to zero. So let me write it down again. It is not necessary that the range of integration of equations 3 and 4 is always from minus infinity to plus infinity Okay, it may be over any domain surrounding the point at which the delta function is not zero. Okay, in general we may write, so in general we may write integration of delta x minus a dx. Okay, delta x minus a. Now this delta function will be zero when x is not equal to a. Okay, and when x is equal to a, this function tends to infinity. Okay, so for this integration, we don't need to take the range of integration from minus infinity to plus infinity. We only need to cover the domain. We only need to take any domain which surrounds the point x equals to a. So we can take the integration range from a minus alpha to a plus beta, where alpha and beta are positive numbers. And in that case, this integration will be 1 for alpha positive and beta positive. This, okay, this is clear. Okay, next now, the function delta x is not analytic, but it can be obtained as a limiting case of either analytic continuous or piecewise continuous functions. That means well, this delta function is not a function in the usual sense of the word function. However, this property can be developed rigorously as a limit of a sequence of functions. I repeat, the delta function is not a function in the usual sense of the word function, but this crucial property can be developed rigorously as a limit of a sequence of functions. That is, it is a distribution. For example, the delta function may be approximated by a number of sequences of functions. Okay, I repeat, that the delta function may be approximated by a sequence of functions. Okay, so let us consider some sequences. So some representations of, okay, let me write it on a new sheet of paper. So some representations of delta functions. Okay. Many representations of the delta function exist, but we are going to consider only some selected representations of the delta function. Okay, that is fine. Okay, number one, it can be represented as a sequence of rectangular functions. So rectangular functions. Rectangular function. Okay, fine. Let me write it here. The simplest representation of delta function. I repeat, the simplest representation of delta function is a limiting form of the limiting form of the rectangular function. Defined as delta nx. This is equal to 0 when x is less than minus 1 by twice n, and this is equal to n when x lies between minus 1 by twice n and plus 1 by twice n, and this is again 0 when x is greater than 1 by twice n. Okay, so when we consider a sequence of such functions for larger and larger n, this rectangular function, it comes closer and closer to the delta function. Okay, this expression can also be written as expressed as say r subscript sigma x. This is equal to 1 by twice sigma for x lying between minus sigma and plus sigma, and this is equal to 0 for x lying outside this range, for modulus of x greater than sigma. Okay. If we take the integral of this, if we take the integral of this function, we'll find that integral is equal to 1. So let us check. Then integral from minus infinity to plus infinity are sigma x dx. This is nothing but since it is 0 for values of x, for values of mod x lying outside this range, so this integration simply reduces to the range minus sigma to plus sigma, because for all values of sigma x less than sigma it is 0, and for all values of x larger than sigma, this is rx is also 0. So only in the range minus sigma to sigma, rx is not, r sigma is not equal to 0, and it is equal to 1 by twice sigma dx. Okay, so 1 by twice sigma, it is a constant. Then we have integration dx is x, and we take the limit from minus sigma to sigma, and this value is nothing but twice sigma. So twice sigma and twice sigma, they cancel out. The twice sigma and twice sigma, they cancel out, and we get this is equal to 1, irrespective of the value of sigma. Irrespective of the value of sigma. Okay, so if we let sigma tend to 0, then the function r sigma x becomes more and more sharply peak, but the area under the curve is always infinity. But the area under the curve is always unity. Okay. So in the limiting case, when sigma tends to 0, in the limiting case when sigma tends to 0, the function r sigma x has all the properties, has all the properties of delta function. So delta x, we can approximately say that delta x is the limit of the function r sigma x when sigma tends to 0. Okay. And let us draw a graph of this function. So if this is the x-axis and this is the r sigma x, so r sigma x is plotted along this y-axis. For small values, or sorry, for large values of sigma, the rectangular function will be something like this. But for smaller values of sigma, it will become more peak like this. And for even smaller values of sigma, it will become more peak like this. So when sigma becomes smaller and smaller, this function goes closer and closer to the delta function. Oh, I forgot to show you the graph of the delta function. This is okay. This is a schematic representation. Okay, This is a schematic representation of the Dirac delta function. So this function is 0 for all values of x not equal to 0, and at x equal to 0, this function sharply peaks to infinity. Okay, this is fine. Okay, now let me stop sharing. Okay, now let us look at another representation of the Dirac delta function. Another representation of the Dirac delta function is the Gaussian function. Gaussian function. Gaussian function. Okay, and this delta function may be approximated by a sequence of such Gaussian functions given by delta nx is equal to n by root over pi exponent, that is exp, minus n square x square. Okay, I repeat that the delta function may be approximated by a sequence of functions given by this expression. That is when n becomes larger and larger, this function moves closer and closer to the delta function. This can also be written in another form as, this can also be written as, this can also be written as z sigma x is equal to 1 by sigma root over 2 pi exp minus x square by 2 sigma square. Okay, so n square is 1 by 2 sigma square. Then let us take the integral of this function from minus infinity to infinity. Then integration from minus infinity to plus infinity g sigma x dx is equal to 1 by sigma root over 2 pi. This is a constant, it can be taken outside. So integration from minus infinity to plus infinity exp minus x square by 2 sigma square dx. Okay, and this integration, it turns out to be, so first let us write down this factor sigma root over 2 pi, and this integration, it turns out to be root 2 pi times sigma. So this cancel out and the final answer is 1. Okay, so that means the area under the curve z sigma x versus x is unity. Is unity irrespective of the value of sigma. Okay, in the limit sigma tends to 0, it is an infinitely peaked function. It is an infinitely peaked function. Thus, z sigma x has all properties of delta function. So delta x can be approximated by limit z sigma x when sigma tends to 0. And let me show you the graph of this. It's loading. Okay. Yeah. Okay, so this is the Gaussian curve, and for smaller and smaller values of sigma, the curve peaks upward. Okay, so this is the Gaussian curve for different values of sigma. You can see that for smaller and smaller values of sigma, the curve peaks upward. Okay, and in the limit sigma tends to 0, this peak will go towards infinity. Okay, so let me stop the recording here.